Hey everybody, we have a problem that would be trivial if this constant over here was 0, of course. We would have solutions minus 13, minus 11, minus 9, and minus 7. Not much of a problem, right? But notice it's not going to be that simple because this constant, well, let me just tell you basically the thrust of this. 7 times, what would be the constant? I'm going to write down what would be the constant if we expanded all this out, then brought the constant 105 back over. So I'm going to leave out the minus signs because they cancel anyway. But the constant we would have would be this large number here. Let me just put minus 105. So you see, an option would be to try to solve a quartic where this would be your constant term, right? You bring him over so you'll have a 0 on the right-hand side, but you would have to subtract this number 105 from the product minus 7 times minus 9 times minus 11 times minus 13. Of course, that's going to be a large constant, probably with a lot of divisors. I haven't computed it. There is common factors here, but in any event, that's not the way to do the problem. There's a much, much better approach here. And one, this you may have seen this trick. Notice that 7 plus 13 equals to 9 plus 11. And this is a pretty common sort of, I think, contest problem maybe. I think a problem like this was purported to be a Harvard entrance exam or something. Maybe MIT, I'm not sure. Harvard, I believe, okay? But notice what happens here. We get this nice condition here. If we multiply the first parenthetical expression by the last parenthetical expression, we get this piece right here. 7 times 13 is 91. And then, of course, we get this piece if we multiply the middle two. All right? And notice there's a separation. They separate by 8. And so you can write this object. And I'm not going to write down a lot of people would prefer to put y here and do a substitution. I'm going to try to get by without doing that. We have this in the difference of two squares form without having to do a substitution. And that's exactly what I've written right here, the difference of two squares. A minus b times a plus b. Nothing says that you have to do a substitution. It might seem easier, but and maybe it is easier, I don't know. But anyway, now look, I brought the 105 back into the problem. Okay, and then we see right here, this is a squared minus b squared, right, equals to 105. Now, and I did leave out a step. If you add this to 105, you get 121, but when you take the plus and minus square roots of 121, you get plus or minus 11, okay? Now, this statement, and you see, y'all, no substitution is happening. Again, let me know what you think. I think it's just fine to avoid the substitution here. So if you subtract 11 from 95, you get the minus 84. You see right here, is that a minus 84? Or did I get that right? Minus, oh God, no, that's not right. That should be plus 84. Yeah, sorry. If you subtract plus 11 from 95, you get 84. If you add 11 to both sides, you get this, right? So you have two quadratic expressions. Now this one here I think works out pretty nicely. You get x plus 6 and then x plus what, 14? Yeah. Okay, equals 0. And of course we get solutions, trivial solutions on this. Well, that's a pretentious word in it, but minus 6 and minus 14, okay, are the two solutions here. Now, notice that a lot of you might have suspected you could do some intelligent guessing and testing here. If you put a minus 6 here, you can see that it'll work, and that's called an intelligent guess and test sort of thing. And similar for minus 14, which you're trying to create a one condition at the endpoints, which isn't necessarily clear unless you maybe look at this constant a little bit more. So you can intelligent guess and test to get the integer solutions, but not all the solutions. Well, I guess you could still, you know. But now, y'all, this piece right here, it does not factor. And so I won't go through the quadratic equation work that you get right here. But what you do get, I believe, and I didn't double check this, but I got minus 10. You can almost do this. You can complete the square here, actually, if you wanted to, real quickly. and get this, but I'll just write the answer down. You get x is equal to negative 10 plus or minus the square root of 6i. And I will take back, so we're finished the problem here. We're done with the problem. Here's the 4 solutions. Here's 2 complex solutions. Then here's 2 integer solutions right here. So there are 4 solutions to this cubic that we never had to multiply out, and it's a good thing we didn't. That would be harder. And also, by the way, if you did intelligent guessing test, you would have been able to do synthetic division or something to get these answers. But I just liked doing the symmetry here without actually writing the substitution down. A lot of you might want to call this, say, u minus 4 times u plus 4. But why do that? Just it doesn't seem really necessary here. It's fairly easy to see the structure without actually having to add an extra variable. Even though I kind of like substitutions in some cases, this doesn't seem like one of those cases. So again, here's your 4 solutions, namely negative 6 and negative 14. And then minus 10 plus root 6i, minus 10 minus root 6i. Okay, that's all.